Greetings to all and welcome to this lecture. We are in module 8, lecture number 3, carrier velocity saturation part 1. In this lecture, we will see what is short channel effect. This SCE stands for short channel effect. So, we will introduce few of the short channel effect, out of which we will discuss about the carrier velocity saturation. These are the learning outcomes of this lecture, which helps you understand what is the effect are coming when you are going from long and wide channel MOSFET from short channel MOSFET. These are termed as short channel effects. We will see the first short channel effect as velocity saturation, or instead you can say carrier velocity saturation, because the longitudinal electric field in the short channel devices will be high, and hence you need to capture the saturation phenomena of carrier velocity. Let us do a quick recap. In the previous lecture, we have discussed that we need to consider the extrinsic effect while modeling the device. This black box or that box is only concerned about intrinsic part, which governs what is depletion, what is inversion, gate charge, oxide charge, etc. However, the overall performance of the MOSFET is governed or given by intrinsic plus extrinsic effect. In previous lecture, we have discussed about a few of the extrinsic effect. We can say as a parasitic effect in terms of source and drain resistances, temperature effect and breakdown. We derived the equation considering source and drain resistances, and we said that the current including source drain resistances RS RD is equals to the current which is not including source and drain resistances divided by 1 plus beta R into VGS minus VT. Here beta R term comprises the source and drain resistances. We said that this is model which is similar as the effective mobility model. However, it is the physical phenomena of series resistances are entirely different than the effective mobility. In addition, we have discussed that the temperature affects your overall performance, because as per of MOSFET is concerned, the temperature significantly affects the mobility and the threshold voltage. Because of that, when you plot the current ID Vg, you will get this kind of curve. So, log square root of IDS, and we got a few curves like threshold voltage increases but current decreases. This is reduced in threshold voltage, this is reduced in current. In both the condition we are increasing temperature. So, at this we will get a ZTC point or zero temperature coefficient point, where a designer needs to operate this device. In addition, we have discussed that we do have a breakdown phenomena, thus the applied voltages in the terminals like gate voltage or drain voltage should be in limit. If you apply the voltages beyond that limit, then there will be a junction breakdown. In some sense, junction breakdown is non-destructive, whereas the oxide breakdown is destructive in nature. In addition, we have also discussed a new flavor of MOS transistor, which we call it as p-channel MOS transistor or PMOS. This is nothing but a flipped polarity NMOS transistor, meaning all the phenomena what we have derived so far based on surface potential, charge and terminal voltages is valid for p-channel MOS transistor as well, but you need to flip the polarity of the terminal voltages and currents. That is what for p-channel MOSFET the threshold voltage is given by this instead of V flat band voltage plus phi naught plus gamma into square root of phi naught for NMOS. So, it is a prime important part which tells us what is the polarity you need to take care of you need to take while designing a PMOS and NMOS in a similar circuit. Let us get started about a short channel effect. Now, what is short channel effect and why the name of short channel effects come into picture? To make you understand, I am trying to make a 3D picture of MOSFET. So, this is N plus, this is N plus, this is source and this is drain. The region between source and drain you called it as channel length. So, between 0 to L you said that this is your channel. Now, if you see the 3D picture, this look like this. Similarly, this will look like this, right. Over this you have an oxide. So, let me make the oxide with different color. So, this is an oxide, and over oxide you do have a gate. So, this is a gate. In this gate you are actually applying the gate voltage Vg, and here you are applying drain voltage Vds. This is source, you are keeping it grounded. This side or this dimension is defined as width of the device, because a MOSFET is in a physical sense it is a 3D structure. So, we do have length, we have width and the oxide thickness, or this is a thickness direction, correct. Now, whatever we have discussed so far, it is all about long channel devices. It means the L is very long. Because of that, we have considered a few of the approximations. Out of which the first approximation we have considered is gradual channel approximation, meaning we said that the channel length is so high such that the electric field in the x direction. So, this is we are taking x and this we are taking y, and I already mentioned that throughout this course we will consider this direction only. This is x and this is y. So, x direction is along the channel length. So, if L is too large, then what will happen? The electric field in x direction will be small, because in general the electric field is can be given by Vds divided by L, which is a horizontal electric field, right. This is small. So, gradual channel approximation is the first approximation with which we started our theory, or with which we started our modeling. We considered that Ex less than Ey, where Ey is the vertical field. In consideration to this, we said that the electron mobility which is moving from source to drain is linearly increasing with Ex. So, we started our analysis considering the drift velocity is can be given by mu into Ex, or drift velocity Vd is can be given by is directly proportional to Ex, where Ex is a horizontal electric field, right. The second approximation we have considered is when we find a current saturation, right, or saturation part of the current, we found that the current is approximately or it is almost constant. It means the current is exactly parallel to the x axis. This term we called it as Ids dash, which is Vgs minus Vt whole square. We said that in this region of operation the drain current is independent of Vds, right, and we only the current is only dependent on effective gate to source voltage. The third approximation we have considered that the length is so large such that the edge effects are neglected. What are edge effects is, we have already said that this is n plus region, the source is n plus region, the substrate is p type. So, obviously there will be a p-n junction, and when you apply the voltages at the source and drain, then you are ultimately making the reverse bias p-n junction, because if you connect Vds positive, it will be n side and this will be p side. So, you are making a reverse bias p-n junction. In the reverse bias p-n junction, the expansion of the depletion region will be there, and in our previous analysis we considered that this depletion region expansion is negligible as compared to the length of the channel. That is what we considered, that channel is sufficiently long and wide such that there is no edge effect. We have also considered that oxide, which we called it as silicon dioxide, if we are considering the silicon based MOSFET, then this is a pure insulator, meaning it will not allow the current to flow, and hence we said that Ig, the gate current, under DC analysis is 0. You remember we started our analysis with another assumption that the bulk current or the body current is also 0, considering when you apply the gate voltage, then there will be a depletion region, and this depletion region is also acting as a good insulator which will not allow the current to flow in this direction, right, and hence we considered body current to be 0. So, these are the few approximations what we have taken earlier to start our analysis or to model the basic MOSFET. However, when you reduce the channel length or channel width, that is what it called as short channel effect or narrow width effect. In that condition, these all approximations will not hold good. The first approximation, if you see, when the channel length is very, very small, then the electric field is very, very high. So, instead of this channel length, what I am doing is, earlier you have N plus here and N plus here. Now, instead of this drain, I am making drain like this. So, let me change the color. So, this is my new drain, right. So, ultimately you reduce the channel length. If the channel length is reduced, the horizontal electric field, which is Ex is equals to Vds divided by L, will very high, and this Ex is will very high. In that condition, what happens is the drift velocity is not directly proportional to Ex, it will get saturated. That is what we are going to discuss in this lecture. There will be a carrier velocity saturation because of high electric field, right, and which we haven't considered. So, we cannot simply replace Vd as mu times of Ex. We need to model it properly to consider the maximum or saturation carrier velocity. The second approximation also fails, as when you go for deriving a current in saturation region, the current will show some part of slope, right. It means the current is not exactly parallel to the x axis, it shows some slope. If there is a slope, means what? The saturation current is also a function of Vds, right. That is what we are going to see, which is as a short channel effect. Out of which the third assumption is very, very important, because the moment you reduce the channel dimension in terms of channel length and the width, the charge which is present at the edges in the depletion region is now become a shared charge of the gate. Meaning, earlier what happened is you were ignoring this second order effect, or you are ignoring this edge effect, right. But now if you reduce the channel dimension, let me make like this, then what will happen? The expansion of this depletion region is not insignificant. It means you need to consider this depletion region charge, and the charge which is provided by the side depletion region or edges is now contributing with the gate charge. So, the edge effect cannot be neglected. In addition, you can see here we have opted only one dimensional analysis considering the gradual channel approximation. However, when you go for this kind of charge sharing effect, it will be a two-dimensional analysis. So, you need to solve two-dimensional Poisson equation to fit a better result in terms of modeling. There are also a short channel effects, like there will be a breakdown at the oxide, means there will be an oxide tunneling, and hence the oxide cannot be treated as a pure insulator. So, there will be a gate current in short channel devices, right. In addition to this, when the electric field, the horizontal electric field is very high, the carrier gets enough energy, and that carriers are called as hot carrier, like we have discussed in previous lecture about the breakdown. So, there will be a junction breakdown, and hence the leakage current is increases. So, in the subsequent lectures, we will discuss about short channel effects. This is very important when we talk about the modern MOSFET, because the modern MOSFET is a scaled version of our historical MOS theory, where we are reducing the dimensions with proper set of rules. That is what we called as classical scaling rules. So, at the end of this module or the next module, we will see about the classical scaling theory and as well as the modern scaling theory also. In the subsequent lectures, we are going to discuss few of the short channel effects listed here, out of which first is the carrier velocity saturation, what we are going to discuss in this module, in this lecture. We will also discuss the channel length modulation. As I said, that when you draw the current with respect to drain to source voltage in the saturation region, it will show some finite slope. The slope is very, very small, but it simply says that my drain current is a function of drain to source voltage. It is not independent of drain to source voltage. That is due to channel length modulation. We'll also discuss about charge sharing effects in short channel and narrow width devices, and how this shared charge will alter your threshold voltage. That is an important parameter in terms of MOSFET, right? So the VT is get altered because of this charge sharing effect. In addition, we will see the drain induced barrier lowering, which is very important short channel effect when you are discussing about the modern devices. What it means is, in general we say the threshold voltage is a function of VGS, and it should be a function of VGS, right? But when the length of the channel is very, very small, when you increase VDS, this drain field will actually lower the barrier at the source. That is what drain induced barrier at the source channel junction lowering. So if the barrier will lowered, the more number of electrons will come from source to channel, and hence the threshold voltage will decreases. That is an important effect we will discuss in subsequent lectures. There are another like punch through hot carrier effect, DC gate current, polysilicon depletion. In general, what happens is the gate metal of MOSFET can be replaced by a polysilicon layer also. So if this is N plus, this is N plus, instead of making with metal, we will make with a polysilicon. And when you operate this MOSFET with applying sufficient voltages like VGS, VDS, then the polysilicon is also get depleted. So the polysilicon depletion will significantly alter the charge and potential balance in your MOSFET or in the intrinsic part of your MOSFET. That really needs to be discussed thoroughly. There are some other effects like velocity overshoot and ballistic operation, gate induced drain leakage, and so. So let's get started with a first short channel effect as carrier velocity saturation. As I said, that when you reduce the channel length of your MOSFET, which is defined between source and drain, and we have defined with some known terms as 0 and L, where L is the edge at drain side and 0 is the edge at source side. So if you reduce the dimension, what will happen? The electric field, which is longitudinal electric field from drain to source, considering source is at ground at this stage, is what VDS divided by L. In that condition, the carrier velocity which we are considering is not linearly rising with Ex, it will get saturated. To start this analysis, first let me define an important assumption or important consideration to go further, is that the velocity saturation or the drift velocity is associated with drift current, and the drift current is only dominated in strong inversion region of operation. It is not related with moderate or weak inversion, because in weak inversion or in moderate inversion, the dominant phenomena is diffusion. So as per of carrier velocity saturation phenomena is concerned, we will only talk about strong inversion region of model, right? In earlier long channel MOSFETs, as I mentioned, that the channel length was very large, and hence Ex, the electric field along the x axis, is very, very small, and we opted for gradual channel approximation. In that condition, we said that drift velocity is directly proportional to Ex. To remove the proportionality constant, we defined Vd is equals to mu into Ex. This is the general approach we opted when we were deriving the IV characteristic of a MOSFET, where mu is called mobility, and in general it is represented in centimeter square per volt second. We have also discussed about the effective mobility and all. Now what will happen when the channel length is reduces? So the electric field, that Ex, will increase. When the Ex will increase, the velocity of the carrier will no longer be valid as a proportionality with Ex. Ultimately it will get saturated. You can see from this curve we are plotting drift velocity in y-axis and Ex, which is longitudinal electric field, in x-axis. When you increase the Ex, that for a smaller values it is linearly rising or directly proportional, but at a moment when Ex is very, very high above a critical field, then it gets saturated. So I can simply draw this curve with two asymptotes. One is this line which shows Vd is equals to mu into Ex, one is taking as an horizontal asymptote, and this curve would be smooth. This shows the carrier velocity. So I can simply say the carrier velocity can be defined as mu into Ex when Ex is smaller than Ec, and it is Vd max, or you can rewrite as Vd sat. Sat stands for saturation, when Ex is greater than Ec. Here Ec is critical electric field, right. From these equations you can simply find out that Ec can be given as mu into Ec can be given as Vd max divided by mu, correct. So that is what we have discussed here. In general, the values, typical values of Vd max is 8 into 10 to the power 6 centimeter per second for electrons and 6 into 10 to the power 6 centimeter per second for holes. The value of Ec is 10 to the power 4 volt per centimeter for electrons. These are typical values for electrons, and 3 into 10 to the power 4 volt per centimeter for holes. Here these parameters like Ec, right, it is a fitting parameter one can tune to get a best fit of the model and the experimental data. Let us see how can we model or incorporate this effect of velocity saturation in our drain current. So to accurately model the carrier transport under the high field condition, we introduce a simple velocity saturation model and make sure that we are doing for strong inversion modeling, right, because in weak inversion this velocity saturation does not hold good. So we are defining a simple model as Vd is equals to Vd max into Ex divided by Ec divided by 1 plus Ex divided by Ec. Let us do a quick check. If Ex is smaller than Ec, then what will happen? You can simply ignore this term, right, from the denominator. In the numerator you will get Vd is equals to Vd max into Ex divided by Ec. Vd max by Ec is nothing but what? Mu. So you will get the same result, that Vd is equals to mu into Ex, which means the drift velocity is linearly rising with horizontal electric field. Now another is what will happen if Ex is greater than Ec. So very high electric field above critical field, then this one can be ignored and this will get cancelled. Ultimately you will ended up with Vd is equals to Vd max or Vd is equals to Vd sat. So the drift velocity will get saturated. Let us move further and see how can we incorporate this model, a basic model of velocity saturation which is widely accepted from different modeling approaches in our current equation. So as we are going for strong inversion, we can simply say the horizontal field along this direction, right, is can be given as Ex is equals to d psi by dx. This equation we have already used when we were deriving the current equation for drift component. You remember that when we were deriving of IDS1. Here as we are actually explaining for strong inversion, this surface potential can be written as phi naught plus Vcb, where Vcb is the voltage from drain to source with a value Vcbx. When x is equals to 0, this will given as Vsb, and when x is equals to L, this will be Vdb. So we are actually expressing the surface potential changes in terms of terminal voltages. So I can simply replace this d psi s by dx as dVCB, which is a function of x by dx. So now what? My electric field Ex can be written as dVCB, which is a function of x by dx. I will put this Ex value here in this equation, I will get this. So Vd max into 1 over Ec into dVCB divided by dx, this is obviously a function of x, divided by 1 plus 1 over Ec into dVc by dx. Now what happens is, here if you see Vd max by Ec is nothing but what? Mu, we have discussed here, right. So it is mu. Now ultimately you will get a equation how my drift velocity changes with x. X is again the dimension along the channel with a limit of 0 to L. So let us find out the current equation now. We have already discussed the current is can be defined as W into minus of Qi dash into Vd. This is a drift current equation, the basic drift current equation. Make sure at this stage you should not take mu into E. That is what we have taken earlier when we were deriving IDS1. In that condition we said that the gradual channel approximation holds good, but now your Ex is very high and hence Vd is not directly proportional to Ex. So we are just incorporating with that model what we derived as Qi dash. Vd is can be defined as Vd max divide into 1 over Ec into dVCB divided by dx divided by 1 plus dVCB divided by dx 1 over Ec, right. As I already mentioned, this term is nothing but what? Mu. So this can be written as W into minus Qi dash into mu into dVCB divided by dx, and I am just putting this equation at the left hand side, which will give you IDS into 1 plus IDS into dVCB divided by dx divided by Ec. So I have two variables, one is dVCB or VCB, which varies with function x with two limits as VSB at the source side and VDB at the drain side, and x having a limit 0 here and L here. So I can do the integration as IDS is equals to W into minus Qi dash into mu into dVCB divided by dx minus IDS divided by Ec into dVCB divided by dx. So just put dx variable here and put the limit 0 to L is equals to W into minus of Qi into mu minus IDS divided by Ec into dVCB with a proper limit as VSB to VDB. When you integrate this, you will get in the left hand side you will get IDS into L, right, considering IDS is constant throughout the channel, and in the left hand side you will get W into mu into integration of VSB to VDB minus of Qi dash, this is dash, dVCB minus, again considering IDS and Ec are constant, and this will give you VDB minus VSB, and we know that VDB minus VSB can be replaced as VDS. So overall this current can be represented as IDS is equals to integration of VCB or VSB to VDB into W into mu minus of Qi dash dVCB divided by 1 plus VDS divided by Ec into L. In our previous analysis we have defined that this is nothing but the current equation given as IDSN, the non-saturation current equation, right. So we can simply say by including the velocity saturation you can express the current equation as non-saturation current equation what we have derived earlier divided by 1 plus VDS divided by L into Ec, where Ec is the critical field, L is the channel length, Vd is the drain voltage applied. So in general I can rewrite this equation as this, where the numerator what we have already discussed and already derived what it looks like in non-saturation condition, So, IDSN is this without including the velocity saturation effect, but when you are talking about the short channel device, then you should include the velocity saturation effect, and hence you need to divide by this factor 1 plus VDS divided by L into EC. So, this factor is actually captures the effect of velocity saturation. Strictly speaking, this equation does not keep a track of transverse field dependence parameters such as EC and mu, right. The second is the above equation is only applicable in strong inversion, because in weak inversion the dominant phenomena is diffusion, not the drift. Now, let me summarize this lecture. We have seen that when you move from a long channel device to short channel device, various short channel effects comes into picture, and we need to take care with how much accuracy we can save our previous modeling approach to include in the short channel devices. We have seen that a few of the short channel effects is very important to be discussed, like velocity saturation, charge sharing, CLM, channel length modulation, Dibble, etc. In velocity saturation, we said that the carrier velocity is no longer directly proportional to the horizontal field, because the horizontal field is in general can be given as VDS divided by L, and now when you are making L very small, then Ex will be very high, and hence at that condition my drift velocity of the carrier is no longer follow a linear trend, but it gets saturated to a value of Vd max. To incorporate this carrier velocity saturation phenomena in our model, we considered a basic model of drift velocity as Vd max divided by d divided by Ex divided by Ec 1 plus Ex by Ec. By doing so, we got to know that the current with the velocity saturation can be given by the current without velocity saturation, which we have derived for long channel devices, divided by 1 plus VDS divided by L into Ec. So, we will stop here for today. Until then, take care.